So next up we have Dr. Rube Williams, who's Principal of Machine Intelligence Applications at Stratus Perceptions. So take it away.
All right, I'm going to make sure I get this launched. Okay, hi, my name is Rube Williams, and I am CEO of Stratus Perception. What I'd like to talk about is the multiphase flow sensing. I want to thank the organizers for this event for inviting me and all the participants. The multiphase flow, our objective here is to sort of to enable multiphase flow for space. The objective of Stratus in general is to enable exploit AI for aerospace purposes. So we're going to look at the cislunar environment. That's the environment containing the moon and the Earth. In particular, we want to consider the thermal environment on the lunar surface and then the orbital environment. In particular, thermal management and distribution challenges exist for this thermal communication between systems. This will typically be convective and conductive type of processes supporting habitats, systems that are machines that might need to operate within a certain temperature band, or resources that may require some sort of environmental control for viability or sustainability. There's thermal expansion, thermal contraction that can misalign antenna and temperature and cameras, and there's general thermal cycling damage. Now, on the moon, the night time on the moon is about 14 Earth days, and likewise, the daylight on the moon is also approximately 14 Earth days. The nights can go as cold as -200 degrees C. So you can have very long periods of very intense cold on the moon. The one way to manage the thermal environment in space is primarily closed loop convective systems, because convective systems regulate their performance, by turning up the pump or lowering the pump speed. Here I'm showing the space station on the right, and you'll see several liquid loops. These are single-phase liquid loops that are providing thermal transport on the space station. The blue in this case are water loops. They're inside the habitat, and they're using water as the working fluid, because if there's a leak, you don't want the working fluid to be toxic to humans. The other loops are using higher performance working fluids like ammonia or other refrigerants, and they're used for external communication of thermal transport to, for example, from one system out to the radiators to be rejected into space. The astronaut on the left, since Mercury, the astronauts have had water coolant loops under in their garments underneath the spacesuit to help regulate their temperatures. And so we're showing in the plot below that the reliability of mechanically pumped liquid is extremely high. It's used in space, relied on in space, and will be relied on for some time. However, as you scale up these systems, you get high temperature gradients, you get high energy requirements for the pumping, and you get higher mass requirements and due to liquid inventory. There's also another way to do things is capillary pump two-phase. It's like the heat pipes that might be in your computer. These are using satellites and on station and just about everywhere, and they're highly reliable. They're isothermal, so no temperature gradients, no energy requirements, because they have intrinsic pumping through their capillary systems, and so you don't have to supply any energy. However, because of its intrinsic nature, they have low operational range and flexibility. Therefore, once you design a system for heat pipe, is kind of inflexible. This could cause, there are a lot of changes in space systems when you're trying to go from initial mission design to final mission design are things that you may change later. And so, so that flexibility is gone, and then the operational ranges are limited. The ideal, it's been sought after for several decades, is mechanically pumped two-phase. Checks off all the boxes except has never been shown to be practical, has instability issues. And this is what we're going to discuss and then present a solution. The problem with two-phase flow, this is flow with a gas phase and a vapor phase. I mean, a vapor phase and a liquid phase, is that there are these phasic behaviors, these bubbles, these different sizes of bubbles, distributions of bubbles, we call them voids. And they cause these different flow regimes that we might label according to what we see. They're labeled by inspection, bubbly, slug, things like that. However, they carry distinct thermodynamic and fluid dynamic implications. And so here below, you see in the graph here, we see a flow channel. In this flow channel, I have vapors coming in, and it's condensing, and it comes out single-phase liquid. So it goes through a two-phase regime, and it slowly condenses to single-phase. But here on this plot, on the ordinal axis is watts per centimeter square, our heat flux. And we're looking at heat flux versus distance from the beginning of the channel. And we see that there's a dramatic drop in the heat flux as you go to single phase. But then there's this aberration in the middle there somewhere where we have the slug flow, and we have this very high heat flux. And then it drops off suddenly again to bubbly flow, and then it drops off again to single phase. And so you get these very stark changes in thermodynamic and fluid dynamic properties. In fact, slug flow carries can carry significant vibration, although it is highly beneficial in terms of heat transfer. So if we look at the flow regime map, we see that there's on our ordinal axis, we have a gas velocity. This is the speed of the bubble, so to speak. And here we have the liquid velocity. All right, so they can travel at different velocities, and these different speeds, these different relative speeds, gives us transition regions for the various flow regimes. And so to be able to control a system like this, you need to know where you are, be able to maybe independently verify and arbitrate gas velocity and liquid velocity, or at least somewhat independently. And therefore, this becomes a very complex problem. Now, if that's not complex enough, we have the flow regimes are acceleration dependent. So here I'm showing on the left side a flow regime map, and on the right side a quite different flow regime map. But this is for the same system on the planet Earth experiencing 1g. There's no change in the acceleration field of the Earth. However, on the left, the flow channel is vertical. And on the right, the flow channel is horizontal to the surface of the Earth. And therefore, the acceleration field with respect to the flow in the channel is different, and you get different flow regime maps. So this causes a problem for not only orbital systems which are in motion, but also for planetary systems where you may be servicing equipment that may be 1 foot or 2 above another piece of equipment. So just the changes in relatively small changes in elevation, or just the turning of your channel to make those adjustments, can cause disturbances and cause problems in understanding what's going on with your flow. Here I am a few years ago flying in what is notoriously called the vomit comet, and we're doing looking at doing experiments with two-phase flow. And the guy down on the lower right is controlling and trying to find the right test point. Now we got about 20 seconds to get our data, so he has about 4 to 8 seconds to get the flow regime right. But he's an expert, and but everybody, we can't just launch an expert like this into space every time we want to run two-phase flow. So our solution is a convolutional neural network attached that's running an object detection algorithm, and it gives us an ability to monitor the flow, track the flow phenomena in high detail. We can get to just about any types of detail, lots of different types of phenomena, more than you could even do with a person. And this gives us the ability to characterize the flow, and then we also get dynamics from the object detection. So we can supply these identifications and dynamics to physics programs downstream, and we can get quite the explosion of quantitative data concerning the flow. Here's some photos of simple object tracking of bubbles, and in the middle there's a sort of a large, what we call a Taylor bubble or slug, indicative of slug flow. And you see the camera there on the right where we're monitoring the flow channel. It's a vertical flow channel. The prototype was developed last year on the SBIR, funded by NASA Glenn Research Center. Here you'll see it's relatively straightforward once the data software is downloaded onto a computer, and then the computer, in this case, has a camera plugged into a USB port. You see cameras can be quite small. This camera runs 1,000 frames per second. And this coin is a 25-cent piece or a quarter for scale. And in an actual implementation, and this is a prototype, but in the actual implementation, this computer would be quite small. This is something we had on hand that's useful for us, and has I think runs a single NVIDIA 2070 GPU. We do the development in the cloud, so this one couldn't support exactly 1,000 frames per second, but straight away maybe about 300 frames per second, and we could do some fancy work with the circular buffer on the camera to get what we wanted. Here we're showing the output to a browser. So you take so this is in real time, and it monitors, and then you can output lots of different data. In this case, we're outputting things like flow regime, void fraction, the phase velocities, the volumetric flow, a quantity called slip, and the flow quality. So and then there's no limit to the types of information that we can extract, because there's been a lot of work in two-phase flow over 3 decades trying to predict and estimate using first principles and empirical models with assumptions, and trying to deal with the missing information. We're supplying the missing information, so there's plenty of physics out there to cause us to be able to extract all types of information out of the flow. And this also applies to general multiphase. Here's another example of a plot. In this case, we're looking at the data in the lab where we were measuring the liquid and vapor flows using Coriolis flow meters. In this case, we're looking here at the gas phase flow on the ordinal axis versus time. And we're comparing that using a 30-second moving average with the sensor. And we're pretty close in agreement within a few percent. Future work, we'd like to demonstrate this technology with control systems. This could be integrated into a control system by providing parameters to that control system, or we can provide and integrate a control system right into the sensor. We'd like to, there's a lot of different directions to go with the technology, so we'd like to develop the technology toward a specific customer goal, so we're interested in a customer. And there's a dynamic power system that's almost forbidden in space called ranking. We'd like to get work with that and maybe bring that to space. Thank you very much.
Thank you, Rube. That was really great. Just a reminder, if you have any questions, please put them in the chat. I was curious, maybe a very basic question, but the camera, are you always able to visualize, the flow inside, whatever it is, where the fluid is flowing, or are there challenges in actually being able to see what you need to see?
Yeah, those are challenges. The sometimes this right now this is specified for flows that are relatively transparent, where you can develop a channel that is transparent.
Gotcha.
You know, so there are other ways to do it. We can, as long as it's an image, we can do thermal imaging through a channel that's, you know, so this technology applies to the image. And so, but right now we're applying it using a video camera. So transparent flows are best.
Makes sense. And you went through your validation really quick, so I may have missed it, but how was that data generated? Was that the data from the vomit comet? Oh, I think you're on mute.
Showing some historical work showing how difficult, how, you know, this problem with multi-phase flows or two-phase has been a problem for a long time, and demonstrating how we would try to manage these to control the flow using an expert that's trying to manage watching the flow visually, and sort of making the analogy that now we're using machine vision.
Gotcha. All right, if there's no other questions, thank you very much. It was extremely interesting. We'll move on to our next talk.
Thank you.